A self-driving car processing millions of data points a second to stay on the road relies entirely on its hardware brain, and that intelligence is dictated by the physical architecture of the silicon inside it. When engineers build these brains, they have to choose between two completely different paths: programmable logic blocks that can change their shape, or custom-forged logic that is permanently frozen in silicon. This creates an immediate dilemma. You have to decide on day one if your project requires the ability to adapt its hardware after it launches, or if you need maximum efficiency to produce millions of units at scale. You are choosing between the agility of a field-programmable gate array, an FPGA, and the absolute optimization of an application-specific integrated circuit, an ASIC. To understand which route your project needs, we are going to measure their performance metrics, trace their diverging design pipelines, map out where industries use them, and define their separate career tracks. Getting this hardware choice right dictates your budget, your timeline, and whether your final product actually survives in the market. This diagram shows the grid inside an FPGA. It is essentially a blank canvas built from lookup tables, or LUTs, and a massive web of interconnected routing pathways. By loading a configuration file called a bitstream, you literally rewire those physical connections. You can create an entirely new hardware circuit in seconds. But that generic grid takes up physical space. Signals have to travel further to get where they are going, which means the chip draws more power and runs at a lower peak clock speed than a dedicated circuit. Contrast that with an ASIC, like this Apple M1 processor. It is engineered from scratch, down to the exact placement of individual transistors, with zero wasted space. Because the hardware is permanently forged for one specific job, electrons have the shortest possible path. That precision delivers extreme clock frequencies and ultra-low power consumption. FPGAs deliberately trade away that absolute peak speed and battery efficiency. In exchange, they give you the luxury of infinite architectural do-overs. This flowchart tracks how both technologies actually get built. They share the same starting line. Engineers write RTL code in a language like Verilog, and they run software simulations to check the logic. From there, the FPGA branch is incredibly short. You synthesize the logic, let the tool place and route it on the grid, and spit out the bitstream file. You load that file straight onto a physical board on your desk. If it fails, you tweak your code and flash the board again 30 seconds later. The financial penalty for a mistake is practically zero. The ASIC branch is punishing. You have to map physical clock trees, route dedicated power grids across the chip, and run exhaustive timing analyses to ensure millions of logic gates fire perfectly in sync. All of that leads to a deadline called tape-out, where the final design files are sent to a multi-billion-dollar semiconductor foundry to be physically manufactured. Once that silicon is printed onto a wafer, it cannot be fixed. A single unspotted bug renders the entire production batch completely useless. The FPGA pipeline allows you to rapidly iterate on a design. The ASIC pipeline is a multi-million-dollar exercise in extreme risk management. Look at this quadrant chart. Companies map their hardware decisions based on two factors: how many units they intend to sell and how often their core algorithms need to change. If you are launching space satellites or deploying edge AI nodes, you need hardware that can update its logic remotely while sitting in orbit. That requires the flexibility of an FPGA. If you are manufacturing millions of smartphones or automotive sensor arrays, you need every ounce of battery life and the lowest possible cost per unit. That pushes you firmly into the ASIC quadrant. Modern data centers operate in the middle ground. They deploy programmable chips to adapt to shifting networking protocols, right next to fixed custom chips that handle massive bulk data processing. In industries like cryptocurrency mining, raw calculation speed is the only metric of survival. The math is fixed, and the sheer volume of computation justifies the massive upfront cost of custom silicon. Tech giants design their own specialized ASICs to process artificial intelligence for the same reason. That level of hardware optimization acts as an economic moat their competitors simply cannot cross. Those custom chips rely on a massive, highly consolidated global fabrication infrastructure. Smaller companies often cannot afford the millions of dollars required just to secure a production slot at one of these foundries. Basic economics drive the choice. You deploy FPGAs when your mathematical models are still evolving, and you commit to ASICs when your algorithms are proven and you are ready to scale. This scorecard lays out the specific skills you need depending on which hardware ecosystem you choose to enter. The FPGA path relies on rapid prototyping. You focus on tools like Vivado, write timing constraints, and prove your skills by building physical working modules, like a UART controller, directly on a development board. The ASIC path prioritizes flawless execution. You master massive scale simulation, heavy Linux scripting, and advanced testing frameworks like UVM to prove the design is mathematically perfect before it goes to the foundry. Because a single physical defect costs a company tens of millions of dollars, ASIC verification engineers who can guarantee a clean tape-out command some of the highest salaries in big tech. When planning a product, you have to weigh your upfront capital against your tolerance for iteration. Choosing between an FPGA and an ASIC dictates your workflow, your engineering team, and your budget. It is the architectural decision that defines the entire risk profile of your project.